Hello once again, pre-calculus students. It's time to look at today's video here and get started with that. So we are going to be looking at 10.4. We are going to look at binomial and weighted probability. So looking at a couple different types of probability situations. One of them is, I think, binomial probability is very useful. Weighted probability also has a lot of uses too. So these are important topics here, but it will only take us one day to go through this section, so let's take a look at them. So first, let's talk about a concept called expected value. What do we mean by expected value? Expected value is what we mean by the average value of possible outcomes. So for instance, if we look at all the possible outcomes and then we average them together, that would be our expected value. So for instance, this would be like calculating and saying, what would be the expected value that you should have on a test or something of that nature? Or expected values for, what's the logical thing to expect when we look at that? So what we have to do is we have to look at a probability model. And our probability model looks like this. So for a probability model, we start with 1 and we go up to n, and we look at what the probability of each individual item is. And we know that a probability model, if we add up all the possible probabilities of the different occurrences, all going through 1 through n, that it has to be equal to 1. That's where that's what makes the probability of something that is certain to happen. If we basically add up all the possible outcomes, it's got to equal 1. And so this is our indication there. That's the probability of each individual event. And then finally, binomial probability. So we're just defining some things here. Binomial probability, this is used when we have repeated events with the same probability each time. And so then we want to talk about what's the probability of a given number of them, particularly happening. So a great example of this is things like where we want to talk about free throw shooter, where let's say, for instance, they have an 80% chance of making a free throw, and then they're going to take 10 shots. Well, what's the probability they make 5? What's the probability they make 4? What's the probability they make, at least 6? Something like that. Binomial probability becomes, so this is when we're going to repeat something over and over again, but we know it has a consistent probability. So it could be flipping a coin. It's 50% probability each time, whatever the case may be. So it becomes very valuable when we're looking at that, when we know the probability of something, occurring. All right, so let's go ahead and let's take a look at the pattern here for binomial probability. This is why we call it binomial probabilities. When we look at this pattern, we're going to see it follows the pattern of the binomial theorem. That's why. So the probability of A, that some occurrence happening, R times in n trials. So in other words, if we think of the free throw shooter example, if you shoot the ball, 10 times, what is the probability that it happens like 7 makes in 10 trials? If the probability of A equals P for 1 trial, so in other words, this P is what we've got, that's the probability for a single trial. So for instance, if we have a 70% shooter and the probability of a made shot, that P there would be 0.7, that idea there. So probability of A happening R times is going to be NCR. Remember, this is our shorthand for NCR here, times P to the R times 1 minus P to the N minus R. Okay, in other words, just kind of as an example here, I will see it when I start to work some examples. It'll become pretty easy. This is the probability of it happening, and it's to the R power, the number of times you want it to happen. This is the probability of it not happening. Okay, the 1 minus P would be the probability of it not happening, and then the N minus R, that basically is the difference between the number of attempts you make and the number you hope that it happens to that power there. And then this is our NCR. So notice this is exactly the binomial theorem. It was NCR. This was our first term, our A to the R. And this was our second term, our B was here to the n minus r power. So let's look at how this actually works. So let's look at some examples. So here's example number 1. So looking at example number 1, I need my book, which is in the other room. One moment. Sorry that took a second. I can't pause my videos when I'm doing them on YouTube, and this is the most efficient way to get them uploaded, so I can't pause it while I go grab my book, and I certainly don't want to restart it, so I guess we just had a little bit of a gap there. So let's look at number 1. So for our example here, so looking at number 1, what we see illustrated is it says find the expected value of this random variable. So notice what we see here is we see that that the probability of getting x, when we look at the probability of getting a 10, that happens half the time, 0.5. The probability of getting a 20, well, 20 happens 0.3, so that happens 30% of the time, and 30 happens 20% of the time. So we have these 3 possible outcomes. We could get a 10, a 20, or a 30. And we know that though it happens in those particular percentages. So what I have to do to find the expected value is I have to go and find the total, the average basically of all the possible outcomes. So if I look at 10, the probability of getting a 10 is 0.5, so I multiply that, and then I add to that. The probability of getting a 20 is 0.3. And then the probability of getting a 30 is 0.2. So those are the probabilities of each individual thing. So I'm averaging them together. When I add all that up, notice what I'm going to get is I will get 17. So I will get, when I add those up, I'll get, the 0.5 times the 10 gives me 5. The 0.3 times the 20 gives me 6, so that's 11, and the 0.2 times the 30 give me another value of 6, so I end up with 17. So when we say the expected value, we know in this case here that that would be what we would expect based on the number of times each one of those numbers comes up. So that's how we would calculate expected value. Let's look at number 3. Number 3 is another type of expected value. It says a game involves earning points by rolling a special 6-sided die that says 5 on 3 faces, 10 on 2, and 25 on the 6th. What is the expected number of points a player will earn by rolling this die? Notice if you roll this die, the only thing that you can get is you could either get a 5, a 10, or a 25. But when we say expected value, what we're saying is, okay, if I do this a whole bunch of times, on average, how many points am I going to get? So it may be a number that you can't even get. You can only get a 5, a 10, or a 25, but on average, when you do this, what are you going to get? Well, notice that I've got a total of 6 faces, so 3 of the 6 have 5s. So I will take the 5 times 3, and then I will take the 10 times 2, because 2 faces have that, plus 1 times 25 and divide it by 6. I could have also divided this by 6 and then added this divided by 6 and added this divided by 6 and divided by 6 each time, because once again we're adding up fractions, and so that would also work. And when I do that, notice here's my other way. Like I said, I could have divided by 6 each time. That's the other way that it would work. But regardless of which way I did it, I would get the same answer when I go ahead and do this. And I would get 10. So my expected value is 10, which actually does happen to be one of the individual values on the dice. So that's what I would expect to get over time. But interestingly enough, notice that 10 is not the most frequent thing that I would get. But because I'm getting 25 occasionally, 10 becomes the expected value that I would get. All right, let's look at number 7. So if we look at number 7, we've got a fairly long reading on this here. So let's take a look. It says, at a carnival, people say that the great Flubini, they pay the great Flubini $2 each to try to guess their weights within 5 pounds. If he guesses successfully, no prize is given. If he is off from 5 to 10 pounds, participants get a prize worth $5. If he is off by more than 10 pounds, participants get a $10 prize. The Flubini is correct 72% of the time. He's off from 5 to 10, 21%, and he's off by more than 10, 7% of the time. If the great Flubini guesses the weights of 300 people per day on average, is the carnival making money, losing money, and how much per day? So what we see comes in here, so it says that he guesses on average 300 people per day. And since they each pay $2, basically the carnival's making $600. The question is, are they having to pay out more than $600? So we want to find out what is the expected payout based on these numbers here. So notice the expected payout, so the income there is $600. Now I have to calculate the expected payout. So as I look for the expected payout, I know that basically it says 72% of the time he's right. So 72% of the time there's no expected payout. So the question is, how about the times when he's wrong? Well, it says that 21% of the time he's off by 5 to 10, which means that they would have to pay out a $5 prize. So 21% of the 300 people would have to be a $5 prize. So this calculates the amount of times that it would likely happen that they would have to do a $5 prize. Plus, it says that 7% of the time, so 7% of those 300 people, they have to pay out a $10 prize. So calculating this, the expected amount they would have to pay out is $525. So notice they are making money. Their expected payout's $525. Their income is $600. So they're expecting to make $75 a day is what they would expect to be making. So that would be the expected amount that they are making. And you could figure out the average amount they would pay out per person, because if you figured out here, what you would have is you would take this 525 and divide it by 300. And if you did that, you would end up getting the amount that they were paying out on average. And what you would find out is the amount they're paying out on average is not an amount. They either pay out 5 or they pay out 10, but the amount they pay out on average is actually less than $2. That's why they're making money. It's because they're bringing in $2 for each person. So all interesting things to look at. All right, last one here, number 21. Deals with our binomial probability. So looking at 21, it says that suppose that a light at the driveway leading to your school is red for 40% of its green, yellow, red cycle during a 10-day period. What is the probability your school bus has to stop there exactly 5 days? So that means it has to stop each of the 5 days that it would run, because we're assuming the bus is only going 5 days. Oh, sorry, during a 10-day period. So it's 10 total times that you're going to be measuring, and we're going to be curious if it has to stop exactly 5 times. So we're talking about the probability of a red light happening exactly 5 times. That's what we're looking at. Probability of red happening 5 times. So going to our formula, we know it's going to be NCR. So our number of times is 10, and we're wondering about happening 5 times, so we run our NCR there. That's our combination formula. The probability of a red light happening, notice it says that red for 40%, so that's going to be 0.4 raised to the 5th power. The probability that it's not red then has to be 60%, so it's 0.6. And if I take 10 minus 5, that would also be to the 5th power. So going ahead and punching this into the calculator and calculating, I would get 0.201, or 20.1%. So the probability that you would hit a red light on exactly half of the days is just 20%. Now, part B says, okay, how about on at least 8 days? So notice at least 8 days means that you have to calculate what the probability is for getting a red light on 8 days, 9 days, or 10 days. So I've got 3 different probabilities. So first I'm going to figure out the probability of a red light. So at least 8. I'm going to have to figure out the probability of 8. So that's going to be 10C8. My probability of red is 0.4. So for 8 times, I'll raise that to the 8th power. The probability of not red is 0.6, and that would be raised to the 2nd power. These two numbers here always have to add up to your total of trials there. That's just from the binomial theorem. Calculating that out there, and then I'm going to go the probability of 9 reds is going to be 10C9, 0.4 to the 9th, and 0.6 to the 1st. I didn't write the 1 there because it's just the 1st power, plus the probability of getting 10. By the way, 10C10, I hope everyone knows that's just 1. So this is just 0.4 to the 10th. Because then, if you want to think of it, there's a 0.4% chance, and it's going to happen. You want to happen all 10 times. So it's just 0.4 times 0.4 times 0.4 10 times. Anyway, you can. That's it done with the formula. Notice 0.6 would be to the 0 power, which is just 1. So I didn't bother to write that there. So adding all these up, we get that there is a 0.0123 probability, or 1.23%. Remember, whenever we have percents that are less than 10, we want to go out to 3 digits of accuracy. So 2 decimal places on our percent there. So 1.23%. So very unlikely that you're going to hit a red at least 8 times. Not very likely in that situation. All right, let's go ahead and let's give you your assignment. So pretty straightforward there. 10.4, 2 through 22 even. So go ahead and get that done, and we'll have one more video notes, and that will be coming out tomorrow, and that will be it for all the material we're learning, and then we're just reviewing. So a reminder to seniors, let me know today whether you want to take the final early on Friday. I've had one senior say they'd like to. Otherwise, if you don't tell me anything, you will be responsible to take it the next week on the Friday with everybody else. All right. Hope it goes well.